All right, so we're going to talk free fall, right? Shh, gentlemen. Herbie, you got your notes ready to go? So last class, right, we did the activity where we tossed the ball up, right? And then we on the motion detector, and then we caught it, right? And we looked at the data, correct? So what we've done is we've taken all that 1D motion that we've been dealing with, right? And we turned it, instead of going horizontally, we've turned it to go vertically instead, okay? So the main thing with free fall is that this occurs when only gravity is acting on an object. Right? So it only occurs when gravity is acting on us. Okay, so that's only going to happen when something is falling, right? Or we throw it up in the air, or anything like that. Anytime it's in the air and no one's pushing it, right? We don't have like rocket boosters on the thing, whatever it may be. It's only gravity is pulling down on it. That's when we're in free fall. Okay? And from the homework that we talked about today, okay, we found out a few different relationships that we can come up with and that we had when we tossed the ball. Okay? So the first one is, remember when we tossed the ball, what did the shape of the distance graph look like? Yeah, it was like an upside down U, right? So we had the graph that looked like this, right? Instead of a U, what mathematical term could we use to describe this? It's like a parabola, right? So it's parabolic. Okay. So if we want to know what the distance an object travels, right, when it's in free fall, so if we throw something up, right, or if we just drop it out of a plane, whatever it may be, the distance that we're going to have it travel is equal to this thing of d equals 1/2 gt squared. We're going to get to that. Okay? Yes, this is something you need to know. Yep. Okay? So this g is very important. All right? This g is very important. All right? Or not. Okay? So do you remember when we looked at that acceleration graph? Right? What was that value we came up with for the acceleration, the average acceleration when it was on that flat horizontal piece? Do you remember? So we had the acceleration graph and the average acceleration when it was at that zero slope line. What was that number? Anybody remember it? It was negative something. Yeah, it was negative 10, right? It was negative 10. So that's what every single object accelerates at, right? Is that negative 10. And that is what we're calling g. So that's negative 10 meters per second squared. So here's the nice easy thing. Anytime you see the letter G, anytime you see G, you're plugging in negative 10. Okay? Simple, right? Anytime you see G, you're plugging in negative 10. Easy, right? Easy. Okay? So if we look at this equation, if we want to know the distance that something's going to travel when it's falling, this is just a number, right? 1/2 times 10, right? Negative, it gives you negative 5, right? So the only thing that the distance depends on when it's falling is the time. That's pretty simple, right? Pretty cool, right? So the only thing that matters or has an effect when an object is falling is how long it's going to fall for. Okay? Now, if you throw some like rocket boosters on there or a jetpack, you're changing something, right? If someone starts pushing the object while it's in free fall, then you're changing this how it works. But as long as we're just dropping the object and it goes like that and falls to the ground, the distance that it travels is only dependent on the time that it falls for. It's pretty simple, right? Pretty simple. Okay. Let's go up here. Now, does anyone remember what the speed graph looked like? What did the speed graph look like? Anybody remember? Yep. Yeah, it was a positive, right? Yeah, so it went down like that, right? So it went down like this. Yeah, so it had this negative slope line, but it was a straight line, right? All right. So this line is linear, right? The line up here was parabolic, but this is linear. Okay? Times t. So if I want to know how fast the ball is falling or any object is falling, it's just gravity times time. Okay? Pretty simple, right? Jared, pretty simple? We got it? Okay? So again, you're looking at these two different things, and these are like the two main things. We've looked at like three things when it comes down to it. We've looked at acceleration, we've looked at the distance something travels, right, and we've looked at the speed. No matter what's happening, whether it's in free fall or it's a car running down the track or whatever it may be. Now, we already know what the acceleration is going to be. We've already seen the distance, and now we've got the speed here. All these things, the only thing that matters, right, or the only thing that affects the distance and the speed is the time, right? That makes sense, right? So that's pretty quick. If you know the time, you can know how far it's going to fall, and you can know how fast it's going to travel anytime that the ball is in free fall. Remember, free fall is when we throw something up in the air, or we drop it, or we throw it down. Okay? Make sense? Okay? So let's say we've this guy, and this is where my excellent art skills come in. And he takes a ball. All right, take a basketball. Right? So he's got this ball, and he drops it. Right? He just drops it, and it falls. And he's got a timer, and he times it, and he finds out that it takes 3 seconds to hit the bottom. All right, so it takes 3 seconds for the ball to go from the top all the way to the bottom. Okay? So what he wants to know in this 3 seconds is how fast is it when it hits the ground? And then how tall is the cliff? Okay? Think we can figure that out? Yeah? So he wants to know again, how fast is it going to be when it hits the ground, and how high up is the cliff? Because maybe he wants to know, maybe if he decides to, maybe something happens and he falls off, he wants to know, will he survive, depending on how high the cliff is. Okay? So if I want to know how fast it's traveling, it's just v equals g times t. G, remember, is -10, and the time is 3 seconds. So if he falls for 3 seconds, the ball falls for 3 seconds, how fast is it going when it hits the ground? Yeah, -30 meters per second. Now the negative sign, again, just means that it's traveling in the downward direction. Okay? So it just means it's going in the downward direction. The next thing he wants to know is, how high up is that cliff? So again, 1/2 times -10, and then t is 3, and we square that. So 1/2 of 10 is, right, 1/2 of -10 is -5. 3 squared is 9, right? So 5 times 9 is 45. So by just knowing how long it takes for the ball to fall, we know that it's going to travel 30 meters per second when it hits the ground, which is fast, really fast. And that the cliff, right, or the bottom, we'll say the cliff is 45 meters up from the ground. Okay? So this g equals -10. And this gets back to what acceleration means, right? This g equals -10 meters per second squared. That means, right, that every second an object is going to change its speed once in free fall by 10 meters per second. So every second it's going to go 10 meters per second faster, 10 meters per second faster, 10 meters per second faster. Or it could be 10 slower, slower, slower. You follow me? Okay, so that's what that means. So essentially it's saying it's going to change 10 meters per second every second. That's what that's telling us. Now, if it was like, say we're on the moon, right? G on the moon is negative 1.67, right? So if it's 1.67, that means when you drop something, it's going to change its speed 1.677 meters per second every second. So it's going to fall more slowly. There's a video, you can look it up on YouTube. I think it's Apollo 17, where there's an astronaut, he's on the moon, and he takes a hammer and he takes a feather and he drops them both. And really it's more of an experiment about air resistance and do objects really fall at the same rate. Right? So he takes a feather, it's a pretty big feather, you can see it, and a rock, and he just goes boop, and he drops them, and they both go boom, and they hit the ground at the same exact time. Right? The interesting thing about it in terms of this difference in gravity, where the moon is a sixth of the Earth, is that, if I take a hammer and I drop it on the Earth, it goes boom, and it falls pretty quickly, right? If it hits your foot, it hurts and all that stuff, and you're angry. When he drops the hammer and the feather on the moon, it just goes. It almost looks like it's floating down, right? Because there's less gravity, right? So it's not accelerating as much. So it's not traveling as quickly as it's falling. It's kind of interesting. It's really weird. Now, if you went on Jupiter, right, where Jupiter's gravity is like 3.5 times this, probably I think it's a little bit more than 3.5 times. It's like 35, 36, 37 meters per second squared. You drop the thing, it's right away, right? After 1 second, it's going 35 meters per second. Right? That's really fast. Imagine that you drop it and you're going over, say, probably over 60 miles an hour. So if something falls for 1 second, when it hits the ground, it's going 60 miles an hour. Crazy, right? Though you'd never make it to like the surface of Jupiter. You'd get like halfway there and then you'd be crushed. Because gravity is so strong, or Jupiter's gravity is so strong, and we're not built for that, and we can't really build many things for that it gets to one spot and it just goes, and it gets crunched up like a can, like stepping on a can. But it's kind of cool. All right. So this is really important. We want to keep this in mind, that things change when they're in free fall. They change their speed by 10 meters per second every second. Okay. So if we go back to our gentleman dropping the ball, we know that right here at the bottom, the ball is going to be traveling 30 meters per second. What if I go up 1 second, right? We'll say that 1 second is right here. So it's fallen for, and this is another second, so it's fallen for 1 second, 2 seconds, 3 seconds. How fast is it traveling after 1 second? So just right here, it's fallen for 1 second. How fast is it? Right, it's 10 meters per second. Okay. How about after 2? 20, right. Right, so every second it's just changing by 10. Now let's look at, dropping's pretty quick, pretty simple. Let's say our guy now, he's got his ball. He's looking a little slim, right? Takes his ball and he throws it up, and then it comes back down and he catches it at the same spot. Okay? What I want to know is, excuse me, and he's going to throw it at the same speed that the ball fell at when it was at the ground. So he's going to throw it at 30 meters per second, really fast. He's a pretty strong guy. Okay, he's going to throw it at 30 meters per second. I want to know what is the speed, right, at every instant up until it stops. How long does it take to get to the top, right? And then how long does it take to get back down, what the speeds look like there. Okay? So we're going to go by second intervals and see what happens. So he throws it at 30 meters per second, so that's going to be right here. All right, so we're going to go 30, right, and then we're going to go, after 1 second, how fast is it going? 2 seconds, 3 seconds, 4 seconds, all that, okay? So after 1 second, it should be somewhere up here, right? How fast is it going? What do you think? Any ideas? First question, is it speeding up or slowing down? Slowing down, okay. How much does an object in free fall change every second? 10, okay. So you know it's slowing down and it's going to change by 10. So what should this be after 1 second? So if I slow it down and it changes by 10, this 30 should become 20, right? So after 1 second, it's now traveling 20 meters per second. Okay? So add another second, right? The next second interval, how fast should it be going? Right? Now it's going from 20, it travels another 1 second, so its speed should be changing by how much? 10. So now this speed should be 10. Okay? Now we get to the tippity top, right? Its maximum height. It's at the top of its path. It's gone up. It's right at what they call the apex, the maximum height. What should its speed be? Very good. 0. 0. Okay? Now, it's coming back down. What should its speed be over on the... It's fallen for 1 second now. It's at the top, and now it's coming back down. What should its speed be? Yes and no. What direction is it traveling? Up or down? Yeah, it should be negative, right? Because it's traveling downwards. Good. All right. A second after it's gone to 10, negative 20. I think you guys are getting it. And then it's come back now to right. It's fallen for another last second, and then now the guy's caught it. He's caught at the same height that he's dropped it. He's thrown it from. Negative 30, right. There we go. So you should see here that when something goes up, when it goes up and then it comes back down, right, the time to go up is equal to the time to go down. Right? So if you know that it takes a certain amount of time to go up, it's going to take the same exact time to come back down. Okay? And at the same time intervals, they have the same speed. Right? So if it's gone up for 1 second, when it comes at the same height, I should say, at the same heights, they have the same speeds, whether they're going up or whether they're going down. Okay? And an interesting thing is that if you know how fast the balls got thrown for, then you know how long it's going to take to get to the top. Right? In this case, it was 30 meters per second it was thrown at. You divide it by 10, right? It means that we've got 3 seconds to get to the top. Okay? What if I throw it at 37? How long is it going to take to go to the top? If I throw it at 37 meters per second, how long is it going to take to get to the top? Not 3. 3.7, right? Because 37, right, we're going to divide it by 10, gives us 3.7. So 3.7 seconds to go up, 3.7 seconds to go down. 3.7? Because it changes by 10 meters per second every second, right? Got it? Cool. All right. So there's a couple interesting things here that we need to keep in mind, and we saw it on our graph, right? We saw it on the graph that John told us for the speed, right? At some point, it crosses over the 0. So right at this point, what is the speed of the object? Right at this point right here, what's the speed? 0, right? Because it's right at 0. Right? That point corresponds to right here at the tippity top. Right? This is your max height. Okay? So that's our maximum height that we can get. So there's a couple things we know now. At max height, V has to be equal to 0. No matter what. When we are at our maximum height, the tippity top, when we throw an object up, the maximum height, the speed is always equal to 0. Right? Because think about it. It has to stop before it can change directions. It has to slow down and stop before it can change directions. So what is the acceleration at our maximum height? So how is this thing changing its speed when it's at the top? What's that? Someone said something. Maybe not. At the tippity top, what is the ball's acceleration? How is it changing? It can't be 0. What's acting on the ball? What's pulling on the ball? Gravity. What does gravity cause things to accelerate at? -10, right? So it's a little bit of a, it's kind of a trick-ish question, but it's very important. I wouldn't necessarily call it a trick question. So even though the speed is 0, the ball or any object that gets thrown up at the top or any point, it still has an acceleration of -10, or equal to gravity, equal to g, no matter what happens. Okay? Daniel? Because this is speed, this is acceleration. Okay? So the important things here, no matter what happens, gravity is always acting on an object that's in free fall. And it's going to cause any object, whether it's dropped, thrown up, thrown down, whatever it could be, may happen, it's always going to accelerate at the rate of -10 meters per second squared. At the top of our path, right, when it gets thrown up, the maximum height is going to be 0, but it still has an acceleration equal to g all the time. Okay? And we can see that every second, an object is either going to speed up or slow down by 10 meters per second because of that gravity. And if we want to know how fast an object is traveling, the only thing we need to know, either how far it's going to travel or how fast it's going to travel, the only thing we need to know is the time. That's all we need to know. Because then we have v equals gt, and we have d equals 1/2 gt squared. Okay? What do you think? Are we good? Does that make sense? Okay, awesome.